The next section of chapter 4 is going to start to talk about some of the particular reactions that we're going to focus on. And we're just going to do precipitation for today, and then we'll save acid-base for another day. And then oxidation and reduction you did not do in honors chemistry, so we'll spend some time working on that in the next few days. But today we're going to talk about precipitation reactions. So first of all, you need to know the word precipitate. It's one of your vocab words. It just means a solid that's formed from two liquids. So when you pour two liquids together, that you can see through, that they have both the compounds have been dissolved, so they're aqueous. Sometimes those ions will stick together to form a solid. And initially, what it looks like is cloudy. So when you see the word precipitate, you want to think of solid and cloudy. And eventually, those solid particles that are floating around that make it so you can't see through the solution, they'll sink down to the bottom and form kind of like a paste that you could filter out if you wanted to. So if you look at this example, we're starting with sodium chloride, which has been dissolved into water. And remember, AQ really means that you have separate ions floating around in water. We also have silver nitrate that has been dissolved into water, so also AQ. But again, remember that AQ does not mean stuck together. AQ really means dissolved in water and floating around as ions. So when we pour these two beakers into the last beaker, there's a couple of things that could happen. If all of the things remain as ions, so if we have sodium, chlorine, silver, and nitrate still floating around as ions, everything is still AQ, and so we say that a reaction has not happened because we started with floating ions, we ended with floating ions, nothing has changed, so that's when we say it's a DNR. But really what happens when you mix these two together is that the sodium and the chlorine are going to stick together and form a solid, and that is not able to dissolve into water, sodium chloride. So when you get this reaction, we're going to switch the partners and we're going to end up with sodium chloride that is a solid, and then we still have those last two ions. And those are still AQ because they're still dissolved in water. So what happens then is that the silver chloride eventually would sink down here to the bottom and form like a paste down here at the bottom. First, it would just be cloudy as you mix them together. So this is a reaction. So you do have to be careful with double replacement reactions. They don't always react. So looking over here step by step, what you're going to need to do is to break apart any aqueous compounds, because those, like I said, they're not really a compound, they're really floating ions. So notice that from this reaction to this reaction, all they did is break apart the things that are AQs. Then they rearranged them, this is really just switching the partners, and figured out the products. And then once you have your two products, so we knew that they were silver chloride and sodium nitrate, then you need to figure out if something is going to be soluble or not. And you used to have to memorize a very long list of solubility rules for the AP exam, and now I think that they're requiring less and less of you to memorize. So what I want you to be familiar with are some of these basic solubility rules up here. And I'll come back to that in just a minute. But so if you can remember that nitrates, acetates, and ammonium are almost always soluble. So it doesn't matter what they're mixed with. Ammonium is NH4+, not to be confused with ammonia, which is NH3. That's different. But if you have any of those three polyatomic ions, it's going to be soluble. And then the other one that's really helpful is the alkali metals are almost always soluble. So if you have anything in group 1, bonded to something else, there's ammonia, it's on the number 2. They're almost always soluble as well. And then there's a few others that you might see in this class, but you can look those up if you need to. So going back down over here, if you look at those compounds, what you would want to see is if there is something that's insoluble, and notice that all 4 of these right here are all soluble. They're all AQs. So we can rearrange the partners, but it's not really doing anything because they're just floating ions. They started as floating ions and ended as floating ions, and so that's when we say that no reaction occurs. And sometimes we write DNR to say does not react. So what you'll have to do is to practice writing these net ionic equations. The first thing you want to do is to separate anything that's AQ, and you want to list how many you have. So notice right here there was a subscript 2 on the sodium, and now it has become a coefficient that once you write the ionic equation. And that's because when we write it, we're writing how many ions we have. It's not bonded to the CO3. So subscripts imply that things are bonded together. Coefficients just list how many you have. And so once we break them apart, the sodium is no longer bonded to the CO3, and so we're not going to list it as a subscript, but we still need to say that we have 2 sodium ions for every 1 carbonate ion, so it becomes a coefficient. And if you had something, there's not one on here, but if you had a coefficient and a subscript, so like if you had 2 Fe2O3 and you're trying to write that as ions, you would say that you have 4 iron ions. That would be a +3 charge. And you have 6 oxygen ions. So if you were writing the net ionic equation, you would have to distribute that too. So going back over here, notice that they broke up the sodium carbonate, they broke up the calcium nitrate because all nitrates are soluble, they broke up the sodium nitrate, it's aqueous as well, we have an alkali metal and a nitrate, so it's definitely going to be soluble. But then notice this last one is a solid, that is your precipitate, and notice that down here they did not break it into ions. So when you're writing the complete ionic equation, you take anything that's AQ, you're going to separate the 2 ions, and notice that they wrote charges on them. So whenever you separate them, see all these pluses and minuses? Whenever you separate them, you have to put those charges on there to show that they're ions. And then don't forget to list how many you have. So again, subscripts are going to become coefficients. And notice that in this case, we had a coefficient, and so you have to distribute that to the whole compound. So notice that we have a 2 for the sodium and a 2 for the nitrate. It's kind of like when you're balancing, you're trying to figure out how many you have. That's what the coefficient is how many ions you would have. And then again, the only thing that you don't separate into ions is anything that's going to be insoluble, which means it's a solid. And then the net ionic equation, again, net means when you take out the fluff or take out the extra stuff. So if you take out anything that remained as ions, notice that sodium stayed as an ion on both sides, and it should be the same number if you balanced it correctly. Nitrate stayed the same on both sides, and so we can take those out of the equation, and what's left is called the net ionic equation. And be careful and make sure you still have charges on those ions on the reactant side. It won't always be 2 ions coming together to form a solid. We kind of focused on that in honors chemistry when we did it, but you're going to see in AP chemistry it can get a lot more complicated than just 2 ions coming together to make a solid. But we'll do some more practice with those complicated ones later. So let's go ahead and write these reactions. So we have KBr plus lead nitrate. And we're going to switch those partners. Let's take some of this off. So now we have potassium is with nitrate. Potassium is +1, nitrate is -1, so we don't need any extra subscripts there. And then we're going to put lead with bromine. And from the first compound, I can see that lead is a +2 charge because notice there's a 2 on the nitrate. And so I'm going to need to cross that 2 down to the bromine. Now we're ready to see what kind of things they form. So I can tell that the first 2 are both going to be AQ because we have a group 1 salt here. We have potassium, and here we have nitrate. So both of those means that they're going to be AQ. This one will definitely be AQ. We have group 1 and nitrate. And then most lead compounds are going to be insoluble. So watch out for silver, lead, and mercury. They tend to form insoluble compounds. So now we're ready to break them apart. Wait, let's make sure we balanced it. Nope, we didn't. So we need a 2 here, and we need a 2 here to balance the reaction. Now we're ready to write the ionic equation. So I have 2 potassium ions, and I have 2 bromine ions because that coefficient gets distributed. I have 1 lead ion that's a +2 charge, and then I have 2 nitrate ions, and that 2 came from the subscript. The next compound we're going to distribute that to, so we have 2 K pluses and we have 2 nitrates. And then the last compound we're not going to break apart because it is our solid. And that is called the ionic equation. So notice I broke apart anything that was AQ. I put charges on them when I broke them apart, and I said how many I had. So subscripts become coefficients, and coefficients get distributed to the whole compound. Now we can see what we can cancel. Looks like potassium stayed as an ion both times, and nitrate stayed as an ion both times. And so what we're left with is the lead ion combining with 2 bromine ions to form the precipitate. And this is called the net ionic equation, what I have in blue there. And the last section for today is just doing some stoichiometry with these. So notice that it says, first of all, let me show you how I would solve these if I was looking at them. It says calculate the mass of solid NaCl. So first try to figure out what they're looking for. They're giving us information about silver nitrate. And then, and they're also talking about the silver chloride as well. So we're adding sodium chloride to silver nitrate. So the first thing is if you can write out a reaction, that will sometimes help you see what's going on. This is going to be double replacement, so we can go ahead and switch the partners. We're going to get sodium nitrate and silver chloride. Silver chloride is a solid, and so this reaction is going to happen. So notice that all of the information they gave us is about this compound, but they're asking us about this compound. So whenever you have to switch compounds, the only way to do that is with the mole-to-mole ratio. So what we can do is go ahead and set up our fence using our information about silver nitrate. So we have 1.5 liters of silver nitrate. I know I'm going to need moles because I want to use that mole-to-mole ratio. So let's go ahead and do the molarity. We have 0.1, whoops, I want to put it up here, moles of silver nitrate for every 1 liter. So moles per liter, I just broke up molarity into moles per liter. Notice that liters are going to cancel, and we're left with moles of silver nitrate. Now I can go back up to my reaction. Let me make sure I balanced it. Yep, looks like everything is a 1-to-1 ratio. So now I can say that we have 1 mole of silver nitrate for every 1 mole of salt, table salt. So that's going to cancel moles of silver nitrate. We already canceled liters. I put a G, it should be a Q. No, but it's a G, sorry. And last thing that we want is the mass of the NaCl and not moles. So now we can look up the grams per mole for sodium and chlorine, which is 58.45 grams. And now we have sodium chloride. And now the moles will cancel, and we'll be left with grams once you calculate this. So notice that this step right here is the step that allowed us to switch from silver nitrate information to sodium chloride information. And the only way to do that is with the balanced reaction. What I did is I used these coefficients. We don't write the ones, but there are ones right here, and that's where I get that 1-to-1 mole ratio. So the final answer for this, let's see, should be 8.78 grams. All right, and then this last one is going to take way longer than 2 minutes. So I'm going to make a separate video for this last one for you.